Here we will investigate some of the basic image processing functions that we can apply for identifying the very basics of spatial image processing. This will help create a solid foundation for understanding more complex video and image processing. MATLAB has built-in low-level image processing functions in their image processing toolboxes, which typically will be used to conduct such functions when one builds complex systems to achieve image and video processing outcomes. However, here we will be investigating some very basic functions and we will emulate them manually on MATLAB via logic functions that we will write ourselves to achieve some of the equations that describe these basic image processing functions. So one of the first things we can investigate is the concept of a neighborhood. Here we are looking at the for neighborhood function, where a pixel of an image is used and its four adjacent neighbors are looked at from a perspective of its intensity threshold to identify whether such neighbors can be considered to be within the same neighborhood if they are within a certain intensity threshold that we assign to it. So if we jump onto MATLAB, we got a function called getConnected, which aims to achieve this functionality. So here we provide two inputs that represents the pixel of the image in terms of x and y coordinates, and then we provide the image itself and then the gray level intensity threshold, and the output will be a couple of arrays indicating the x coordinate and the y coordinate of the pixels that are considered to be connected. If you spend some time opening this file up, you will be able to look through these pseudocode and understand the detailed code that has been written here. In fact, it is very simple and very basic. A few if conditions looking at each of the adjacent neighbors to see whether they are within the threshold, and if so, we assign them to the output array. It's very simple. So we will jump back onto our main live script and invoke this function. Here I'm calling this function and giving the pixel which belongs to row 260 and column 10 of an image, a reference image, image of an iceberg. It is a grayscale image here, as you can see, which is a very basic function of an image. We've removed any color related aspects to simplify what we are trying to do here. Okay, and then our intensity threshold is set to 10 here. Now we will run this function. Okay, we have run it and we can see that 3 of the 4 pixels belong to its neighborhood based on the provided criteria. Perhaps let's reduce the intensity threshold to 5 and see what we get. If we reduce the threshold to 5, we can see only 2 of the neighboring pixels belong to this neighborhood. And we can take it further where we can look into connected sets. So pixel P and Q are said to be connected if there exists a set of pixels forming a path between those two pixels while also meeting the previously illustrated intensity threshold. So using that logic, starting from a single reference pixel and giving an intensity threshold that we can, or rather we want to test for, we can find a connected set. There are probably multiple ways to achieve this in terms of the coding mechanism to obtain that output. One thing to note is that when implementing that logic, we take the neighborhood feature we discussed earlier a bit further. So earlier we were looking at 4 neighborhood, essentially looking at left, right, top, bottom pixels, but we expand that to 8 neighborhood mechanisms where we look at the diagonally neighboring pixels as well. So that's what we have attempted to do here. We are looking at connected sets, and as I mentioned, there are multiple ways to do it. How we have done this is when a reference pixel is given, the image is broken into 4 quadrants, and then we create some reference matrices. We call it intensity match logical matrix, which takes the same size as the image and have all the pixels as false as default. And then starting from that reference pixel where it meets that intensity threshold of concern, we change it to a true. And then we also have a connected match matrix of the same size as the image, with 0 as the default, and then create a connected set match logical matrix of the same size as well. And then use those matrices to essentially achieve the outcome we want, which has been illustrated in this text here. And we will jump onto MATLAB just to have a look at the actual code. So the MATLAB function for this is called getConnectedSet. So here once again we give the reference pixel as an input and the image of concern as an input and the intensity threshold that we are testing for. And the output will essentially be an array X and array Y of all the pixel X and Y coordinates that form the connected set and the connected image as well. Over here, spend some time to read through the pseudocode if you wish to, and then that will make it easier to understand the code that's been written. As illustrated previously, we've created a few reference matrices that are the same size as the image, and based on some logic that we implement using that 4-quadrant mechanism, we fill out those matrices to obtain the final outcome that we want. This function is probably a little more complex compared to that previous get connected, very simple function. However, once again, the basic structure of it comes down to if conditions and for loops and so on. And here we can see that first we process the data of the first quadrant, and then we jump onto the second quadrant and sort of repeat that logic, and so on and so forth, where we do all 4 quadrants. And then form the final image. So if you go to the live script, okay, let's perhaps invoke this function. And in this case, our input is that same reference iceberg image, and reference coordinates for the reference pixel is 191 on the x-axis and 181 on the y-axis. And let's start with the intensity threshold 10, for example, and see what we get. Okay, so this actual pixel sits somewhere in this part of this iceberg, and we can see that it's got this connected set forming around that reference pixel. Okay, let's bump this up to 20 and see what we get. Okay, as we bump the intensity threshold to be a bit higher, we can see that area of the connected set increasing. Let's bump it up all the way to 50. Okay, now we can see we get a image that is easily distinguishable when we look at the reference image as well. You can see that this area visually has a very similar intensity range. And since our reference pixel is somewhere here, the connected set also takes that form, and it ends at the boundary where there is a much more contrasting change in intensity. So what we can do is now expand what we have done with the finding of connected sets towards region growing, which is used for image segmentation. So that same function that we developed earlier to find connected sets are expanded to find multiple connected sets on an image. So the basic approach here, as we've illustrated on this text, is to start from a set of seed points and grow regions from these by finding connected sets based on a predefined threshold that we provided to the function. So the image will have each and every pixel processed to see whether it already belongs to a connected set, and if it doesn't, that pixel will be used as a seed point and a region will be grown from that particular seed point based on that threshold to create a connected set. And then the program will sequentially move on to the next pixel and see whether it's already part of a connected set. If it is, it will ignore that, move on to the next one, and so on and so forth. So depending on the intensity threshold value that we assigned, the image may end up having a very large number of regions or a smaller number of regions, obviously depending on the complexity of the image and the intensity threshold that we assigned to the function. Similar to the previous function, these two will create multiple matrices that are of the same size as the image that's being processed to achieve the required outcome. So jumping onto MATLAB. So here is an example where I have already invoked this function, which is called segment image with a intensity threshold of 75. And with this one, we see the result here on the right. And there are easily distinguishable regions that can be counted fairly easily. There's about 5 here, 1, 2, 3, 4, and a few smaller areas as well. Let's jump into the actual code. And here our input is the image and the intensity threshold. Contrary to the previous functions, we don't provide a reference pixel because this will scan the entire image, all the pixels of the image. And we can see that this function in itself invokes the previously created getConnectedSet function. And we can see here there are a couple of for loops, one nested within the other, one scanning the number of rows, and the other one, the internal for loop, is scanning the number of columns on each row. And if it finds that one pixel already belongs to an existing segment, or rather a connected set, it ignores that and jumps onto the next one. So if it doesn't already belong to a connected set, then it will try to grow a region from that particular pixel. So it is just a couple of for loops, just running the previously created getConnectedSet function on a repetitive basis. So that's what we have done here. And we have also just done that for a smaller intensity threshold from 2 to 10. It should be noted that when the intensity threshold is much smaller, the process takes a much longer time to run. So this section automatically creates some images where it sequentially increases the intensity thresholds for the images. And here we can see that when the intensity threshold is set to 2, there are 7,059 unique regions. And as the intensity threshold is increased, the number of regions decrease as expected. And here we see that we go all the way up to 10. When the intensity threshold is 10, it's resulting in 833 regions. And we have to go all the way to about 75 for the intensity threshold values to get a set of regions that are sort of comparable to the original image that we have been looking at. And that's what is been sort of illustrated on this graph here as well. As the intensity threshold value increases, the number of regions tend to decrease.